Hello everyone, welcome to the today's session on design aspects of surface drainage system. Here we are discussing on two aspects, that is hydrological analysis and hydraulic analysis. Hydrological analysis is nothing but the calculating or estimating the maximum quantity of water for the design of component of surface drainage system, whereas the method of analysis and design of cross drainage and longitudinal slopes is called, that is hydraulic analysis. I hope the concepts are clear with hydrological and hydraulic analysis. Now first part, hydrological. So here we'll see the objectives of this hydrological analysis. Here the main objective is to find or to estimate the maximum quantity of water, that is in the equation you are seeing, that is capital Q. Capital Q expected to reach the component of drainage system under consideration, such that the roadside drain, the portion of precipitation during the rainfall in the filters found as groundwater, and small portion gets evaporated. This remaining portion of water which flows over the surface is termed as runoff. So the various factors affecting this runoff is that maybe, as I mentioned, the intensity or rainfall rate, type of the soil, moisture content in the soil, topography of the area, type of ground cover, like the type of the pavement surface, vegetation on the adjoining land. The surface drainage system is to be designed to drain away the surface runoff water reaching each component, such as the roadside drains and cross drainages. The following steps we'll see. So that is to collect the details of rainfall in the area, including the intensity, duration, and the frequency of occurrence of stream. To find the drainage area from where water is likely to flow in, and to determine the runoff and maximum rate of runoff for the area under consideration using any of the expected approaches, or to estimate the peak quantity of runoff water reaching the component of the drainage system, that may be side drains or cross drainages, right? So these are the pre-feasibility studies required for hydraulic analysis. So after collecting these all secondary data, we need to sit for the calculations. So here, to estimate the quantity of runoff flowing in the drain, the rationale formula is widely used to estimate the peak runoff water for highway drainage. The simplest equation what we see is capital Q runoff in meter cube per second is equal to the runoff coefficient capital C, which is nothing but the ratio of runoff to rate of rainfall, into I, rainfall intensity in mm per second, capital A small d, ed, that is area of drainage or drainage area in 1000 meter square. It may be noted that this equation is dimensionally not balanced. As per rational formula, the quantity of runoff flowing into the drain depends on the runoff coefficient, intensity of rainfall, and the total drainage area, right? So it is directly proportional. Now we'll see one by one. That is, first, capital C, that is runoff coefficient, depends mainly on the type of surface and the slope. The C value may be taken as say 0.8 to 0.9 for bituminous or cement concrete surface or pavements, 0.35 to 0.7 for gravel or WBM pavements, and zero point 0.4 to 0.65 for impervious soil, and for pervious soil it is very less, that is 0.05 to 0.3. So runoff coefficient, what we have understood is, if it is a pervious soil, it is a very small value. If it is non-pervious cement concrete road or very less pervious bituminous road is there, the value will be higher. And next is the AD, area or drainage area, from which the surface water is expected to flow to the side drain, is determined with the help of contour maps or by studying the topography of the drainage area, and this is expressed in units of 1000 square meter to obtain the value of AD. The value of AD or drainage area consists of several type of surface with a different value of runoff coefficient C1, C2, C3, right? And with respect to the different areas like A1, A2, A3, capital A1, A2, A3. So the wetted area, the wetted average value of runoff coefficient, so that C value what we had mentioned, it is not possible to have a single type of area or cross drainage slope, sorry, uh, natural profile, right? So there may be some area, maybe vegetation may be there in some area there is a lot of slope may be there. So we are dividing the entire area into A1, A2, A3, and like that. And similarly the coefficients what we have discussed, C1, C2, C3 for those particular areas, and we will be calculating the wetted average value of runoff coefficient, capital C, that is equal to, here we can see, that is A1 C1 plus A2 C2, A3 C3, like that, AN CN divided by total area A1 plus A2 plus A3 and till AN, right? Like this we can calculate. And now remaining is small I, that is nothing but the uh, rainfall intensity. So it is not that easy to find, so here we need to collect some of the datas, so that we'll discuss. So here we are seeing the time of flow to inlet uh, chart. The rainfall intensity I, it is depends on various factors as I mentioned. Here the design value of rainfall intensity can be obtained for expected duration of storm and frequency of occurrence. Therefore, the inlet time of the storm water to flow from a remote point in drainage area to drain inlet is estimated using this chart. Here in this chart it may not be very clear. While solving problem, I'll make sure that this chart is easily readable. Here what we are seeing on the x-axis, that is the time of water to flow uh, through the drain between the inlet and outlet points. It is determined based on the allowable velocity of flow in the drain, which is generally in the range of 0.3 to 1.5 meter per second, depending on soil type. So in the coefficient there also we had seen how it varies with respect to the type of the surface. In the other case, the surface to drains and pipe to drains, higher velocity of flow is permitted. Here we can see on x-axis that is time in minutes, y-axis distance in meters, and on above we can see that is pavement or a bare soil, or it is a thin turf or average turf. So with respect to different slopes, these different lines are provided. So with respect to the pavement surface and the slope, we can uh, find the required data. That will be your small t1. And next is t2, total flow through drain, that is time of flow through drain, small t2 is equal to length of the drain divided by the allowable velocity in the side drain will give us the small t2, and total will be small t1 plus small t2 will give us the total required time. Next, the time of concentration or duration of storm for design may be taken as sum of inlet time and the time of flow through drain. The frequency of occurrence of a storm or the return period may be taken as 5 years, 10 years, 25 years, 50 years, like that. So these frequencies are mentioned in years. From this chart, what we are seeing here, it is nothing but the rainfall intensity versus duration curves. So durations we have mentioned 2, 5, 10, 25, 50 or 100 years, and rainfall intensity. The design value of rainfall intensity I is found corresponding to the duration of storm and the selected and duration of time we can calculate. So we can be able to calculate the total quantity, that is Q. Thank you.